So we're going to start now with Phil Lubin will be the next presentation, and I've known Phil for a long time, but I want to look this up anyway. Yeah, he's the professor of physics at UC Santa Barbara. As you know, he's the author of a Starlight program that kind of goes back and was the genesis for that was picked up by the Breakthrough Starshot, which maybe a few words about that as he goes along. But he's a winner of the a co-recipient of the 2006 Gruber Prize in Cosmology, along with the Kobe Science Team, and groundbreaking work in that. So with that, I'll introduce Phil Lubin. Thank you, Phil.
First, I want to say that the discussion we heard on the panel was incredibly important, because without leadership and without support, as was mentioned, we're not going to get very far. We're certainly not going to get out of our solar system with that. So it's very important that we engage the public. And the public wants to do this. I know, because I get letters that are literally from children that say, I want to hold a cupcake sale, literally, that's what they've said, to help make this happen. So we have the support of the public. We just have to utilize it properly. So this is not a math-free zone, and I apologize. Those of you that have read any of my papers know that I'm not a math-free person, and just the way it's going to be. Okay, so this is going to be talking about the directed energy for a realistic way to get to relativistic speeds. And I'm going to show you all the things that don't work, and it's going to disappoint some of you and perhaps really piss off some other people, but I'm not going to apologize for that. It's just physics. Okay, so this is comes out of a NASA program. The whole genesis of this is NASA. We're in a phase 2. This is year 3 of the whole program. We started a phase 1, as I'll show you in a bit, the history of this, which was then picked up in the genesis for the breakthrough program. What's important here is this is actually a path to a very long-term strategic transformation in our capability. It's not an incremental approach. This is a sort of what you'd call a disruptive technology in the parlance of sort of popular ideas about what is disruptive. If you're interested, check out our website. Just look us up. If you're interested in doing your own calculations, there's an online calculator, including a new relativistic calculator that allows you to go into even higher speeds if you're interested. And then if you cannot sleep, I would suggest reading this paper, because it will definitely put you to sleep. So I went back and looked at my opening slides from the last TVIW, which was late February, early March of 2016. And I was just curious as to what I put in that presentation. And here's the opening slide, exactly the same, except I added this, which was directed energy for relativistic flight. NASA had just released their video, which I'm going to show you again. And then a bunch of things here, including the bottom one here, which is a quote from Thomas Watson, which was so far off that it looks ridiculous now. But in fact, that's the way that people are unable to see the future. And that's also the case here. Unless we understand the difference between linear technologies, which were expressed on the panel, and exponential technologies, we will not fully understand why this is a way to go, and probably the only way to go, at least for the foreseeable future. Okay, this was slide number 3, in which one of the things I said is I don't want to be talking about this 20 years from now. I want to be building. So actually, in the last 18 months, we've now moved to the phase we're starting to build. So I'll show you results from our latest laboratory measurements, which I think you'll find quite interesting. And this is still true. It won't be easy. There's a lot of technical difficulties, and it's not going to be cheap, but it is possible. And indeed, it will profoundly affect us if we go this route. So let me just show you the NASA video really quickly. There's some audio here, which you probably have to turn up. Here's the dilemma. We know how to get to relativistic speeds in laboratory. We do it all the time. And then we go to the macroscopic level with things like aircraft, cars, spacecraft. We're pathetically slow. So the question is, can we bridge that gap between what we do now on the macroscopic level with chemical binding energies to relativistic speeds, which are done with electromagnetic acceleration? The shuttle, when it would take off, or the SLS, when it will take off, will have a power off the launch pad of between 50 and 100 gigawatts. Turns out, to get to relativistic speeds with the spacecraft we're talking about, you need basically the same power level. And for about the same amount of time. It takes 10 minutes to get to orbit with shuttle. It takes us 10 minutes to get to 30% the speed of light with about the same power level, just using different technology. We could propel a 100-kilogram robotic craft to Mars in a few days. If you want to push something like shuttle class, it takes you roughly of order a month to get there. Within about 25 light years of the Earth, there's actually quite a few potential exoplanets and habitable things to visit that may be habitable. We don't know, of course. And so there are many targets to choose from. The closest is Alpha Centauri, which is about 4 light years away. So photon-driven propulsion is not a new idea. It goes back to the beginnings of thinking about light in both the classical and the quantum mechanical way. There are recent advances which take this from science fiction to science reality. There is no known reason why we cannot do this. There's a roadmap, which you can look at in our paper, to relativistic flight. The system is completely scalable modular. Build any size you want, from a tiny one to a gigantic one. Okay, so I went back and looked at history and wanted to see what had changed since the last TVIW. So here's a quick synopsis, just for historical reasons. We started this program in 2009 at UCSB. Most of my life is spent in early universe studies, but I wanted to do something a little bit different as a hobby, and so I picked this up as a hobby, and unfortunately got out of hand. In 2013, we started publishing papers, which you can look up, on planetary defense applications and interstellar capability enabled by directed energy systems. And it's all actually, this same system is described in 2013. And we made a press release on February 14th of 2013 because we knew that DA 14 2012 was going to come along the next day, and we wanted to engage the public in a conversation. If you want to look at one single date that started this whole process, it is that date. We had a minor press release because we had a white paper that we submitted to NASA about the capability. One day before, something else happened, which we didn't know was going to happen. Well, the stuff hit the fan the next day because I woke up and my colleague called me, "Did you see that Russia was hit by an asteroid?" And I said, "Yeah, right." But in fact, it was, and the phone kind of rang at that point. We submitted a NASA proposal first in 2013, and they liked it, but they said come back with another one, didn't accept it. So in 2014, we submitted again, which was then funded in early 2015, which is using a phased array directed energy system with the possibility of ultra-low mass spacecraft. And that's exactly, of course, what has been picked up in the popular press as well as with Breakthrough. The roadmap paper actually started in late 2014. It was submitted in 2015 in April. On October 31st, in a random meeting at the 100-year Starship meeting in Santa Clara, I bumped into Pete Worden, literally, just bumped into him randomly, and I told him about our NASA program, which was at the end of a phase 1. He said he'd like to send it to a friend of his. I didn't know who the friend was. So that's kind of an interesting, another date, October 31st, as well as February 14th, different years, of course. Time Magazine came out and filmed us and made a really nice video, which I'll show you at the end. Early 2016, an anonymous donor, who I won't mention because he's anonymous, stepped in and started funding us. Not the Breakthrough Foundation, but somebody else. In January 2016, Yuri called for meetings to discuss the paper, the roadmap to interstellar flight. That was the start of then the whole, what became the Starshot. It wasn't called that at the time, but eventually became that in April. In February 2016, NASA released their going interstellar video, which I just showed you. March 2016, or end of February, was TVIW. I knew what was, obviously, there's a lot I didn't say at that meeting, but it came out later. April 2016, Starshot was announced, which was actually 1,000x leverage of our NASA program, which was great. And at the time of phase 1. Culberson's announcement came out in 2016, which was not related to this, by the way. It was related to our work with NASA and specifically mentions NASA's directed energy program, namely ours. Our phase 2 was announced in May of 2016. The timescales here are incredibly compressed. So to date, NASA should take credit for spawning 3 significant issues. One is the breakthrough issue, And then we have actually 4 issues. We have 3 new NASA NIACs that build off this. 2 on composition analysis of asteroids at standoff distances, and the other is driving ion engines from a distance using beam power. And we have 50 papers if you're interested. All of them, I'm afraid, are highly mathematical and will bore the crap out of you. Okay, so you know that we now have congressional support for this. So I think this is incredibly important for the field, that we now have the interest not only of the public in a scientific manner, but we have the interest of Congress. And in that report, it specifically mentions the NASA program. What I didn't know the last time I was here was that there was actually a planet around our nearest star. None of us knew that, at least none of us that I know. And so that was announced in August 2016. There's likely many more planets in the Alpha Centauri region and in many others nearby. So the program grows for this NASA program, which is now known as Starlight, is to develop directed energy propulsion for high-speed applications, not just for wafer scale, by the way. People misconstrue that completely. To enable relativistic flight for the first interstellar missions, also enable extremely rapid interplanetary missions, such as beamed energy to ultra-high SP engines, which we're currently doing with JPL, and lots of other applications, which I'll get to. And unfortunately, chemistry is not going to work. It hasn't really changed much in 80 years. I'm going to show you an example of that. And unlike chemistry, photonics, like electronics, is an exponential technology with a doubling time of about 18 months. And I'll show you a comparison to chemistry in just a few minutes. There's a lot of things that need to be enabled, but this program is not an all-or-nothing program, and you'll see that we're already beginning prototypes, and it enables many, many different missions, and a huge parameter space gets opened up when you do this, and it leverages very large-scale US and DoD contributions. So those of you who've seen my talk, seen this before, this is speed as a function of mass, of what we as humans have been able to do. At the low end, at the fundamental particle level, we accelerate to within 1 meter per second of the speed of light. At the high end, we're quite slow. This is a log plot, so you can see that we only get to about 10 to the minus 4 the speed of light with chemistry, and down here we get to within 1 meter per second of the speed of light. So there's a big divide in between, which we intend to begin to fill in with directed energy. So one question I get, even from my technical colleagues, is, well, forget going anywhere, just build a big telescope. I mean, why the heck go anywhere? And I think we need to seriously explore this issue and understand it, because otherwise you'll just be fooling yourself. Unfortunately, most people don't realize everything is remote sensing. You are remote sensing me right now. Everything's remote sensing. When you look in a microscope, a telescope, that's all remote sensing. It doesn't matter how far away you are, it's remote sensing. You remote sense your finger, even when it's sticking in your eyes or wherever else you put it. Okay, so no, we don't want to stop building telescopes, but I want to give you a small comparison when someone asks you about why go anywhere. The spot size of the system we're talking about building is about 10 to the 8th meters for a 1 kilometer array, or 10 to the 7th meters for a 10 kilometer array at 1 micron. So we're already building a gigantic telescope. It's a phased array telescope, so it's a little bit different. But let's flip the coin here. Suppose I take a little tiny optic, like a 10 centimeter optic, and put it at 1 AU from a object such as Proxima b, which is a planet around Proxima Centauri. By the way, it does not take seconds to cross the planetary orbit. It takes 40 minutes to cross 1 AU at 0.2 c. It takes 8 minutes from here to the sun, the speed of light, multiply by 5, and you get 40. It's very simple. Okay, so it doesn't happen. It's not all over in seconds. Proxima is about 250,000 AU away, so what would be the equivalent telescope size on Earth? Very simple. Multiply the two together, and you get 25 kilometers on Earth. So if you want the equivalent resolution of something the size of your hand on a spacecraft 1 AU away from a exoplanet 4 light years away, you need a 25 kilometer telescope at Earth. Now let's go closer. We don't have to stop at 1 AU. Let's go a tenth of an AU. Now you're going to need a 250 kilometer telescope. Well, we don't have to stop there. Let's go 100th of an AU, which is about 108th Earth radii away. You're going to need a 2,500 kilometer telescope. Well, go for it. We should do that. Okay, but the costs are going to be daunting. In addition, the system is not launched once every 20 years. You could launch a mission every few minutes for small spacecraft. It totally changes the way you think about orbital missions versus flyby missions, which I know there's been discussion of here. Okay, in Breakthrough, we don't have the power available to do that, so we're going to store energy and then dump it. We do about a mission every day or week, depending on how we build it. Okay, mass ejection propulsion of any kind, whether it's chemical, nuclear, ion engine, doesn't really matter all that much, is not going to work. And it's just physics, and I'm sorry to tell you that it's just physics. So here's a nice example of a Merlin engine on SpaceX, which has an ISP of about 350. Now let's do an extreme example. Let's take all the mass in the universe and convert it into chemistry, and let's have a payload which is 1 proton. How fast can you go? I mean, that's about as much mass as I can imagine dumping into a spacecraft. And the answer is you can get to approximately 180 times the exhaust velocity. It doesn't work. You can't even get a single proton up to relativistic speeds using all the mass of the universe. Okay, so here's an example. Here's 75 years of propulsion. Here's a V2. Since we're in Huntsville, this is possibly a good place to talk about this. This is a cutaway of a V2 from 1943. Here's the SLS in 2017. The ISP, which is a metric of performance, really didn't change. Why? Because chemistry doesn't change. The rockets of 1,000 years ago used basically the same chemical reactions as today. Yes, they didn't have liquid hydrogen and liquid oxygen, but the chemistry is still about 1 eV per bond. So then the efficiency is 10 to the minus 10 at best. Well, here's a 1943 computer compared to a 2017 computer. Same time frame. This one, on the other hand, rather than not increasing in performance, had a billion times increase in performance. This was, by the way, about 500 flops. This is a teraflop. It had 1 trillion times less power per flop, 10 trillion times less cost per flop, and 1,000 trillion times less mass per flop. So there was a little bit of advancement here and not there. Why? Because this is an exponential technology. This is never going to change significantly. Okay, and I know, that's a terrible disappointment to people that build rocket engines that get us places, but you can't get any better than we currently have on the periodic table unless we engineer things at the atomic level. Photonics, like electronics, is exponential. Here's the power out of a single mode fiber as a function of year over 25 years, and I fit a curve to it. It's a nice doubling time every 18 months. Okay, that's like electronics. The way we plan to do this is not build one gigantic laser pointer, which I'd love to have, a 100 gigawatt laser pointer. I could make parking spaces wherever I want, and I could just end arguments immediately. So when people disagree with me, I would just say, thank you, okay, for your opinion. So it's a parallel processing machine. You take a bunch of flashlights, phase lock them. It's like building a supercomputer. You don't build one gigantic CPU, you have 1 million CPUs. Same way we build computing today. So it's called a phased array. It's used in a number of applications, particularly in radar. You build such systems, which are called MOPA systems, master oscillator power amplifier. It's hard, it's difficult. So people in this audience in particular like to invoke fusion, kind of like people invoke other things in life as a solution. It doesn't work. For what doesn't work? It doesn't work for reaching relativistic speeds at any reasonable mass level. It just doesn't work. So as an example here, for those of you that might know anything about nuclear weapons, the best nuclear weapons have a yield of about 5 megatons per physical ton. That gives an engine efficiency of about 10 to the minus 4. Okay, the maximum fusion reaction that we know about is less than 1% efficient. It really doesn't work when you do the math, and I know it's very disappointing to people who want to build fusion engines. They're great for inside the solar system. They're terrific. I'm all for it. It's not going to get you to the relativistic speeds you need. In relativistic to me is greater than 10% the speed of light. Okay, so things that don't work, everything, including fusion, doesn't work. There's only 2 known solutions besides new physics, and one is antimatter, which I would love to have, but you would not like me to have it. Because one of my dreams in life is to have a set of nuclear weapons that I can go out in the desert and blow up just for fun, because I'd like to blow things up. But, well, I'd love to have a kilogram of antimatter, which is about, by the way, the energy equivalent of the largest thermonuclear weapon ever detonate, which is the Tsar Bomba. detonation, which was derated from 100 megatons to 50 megatons, so they wouldn't destroy the aircraft, which they almost did. That was a Soviet weapon. Okay, but the other one is directed energy. But directed energy only works when you leave home without it. Otherwise, it doesn't work. Okay, for those of you that are rocket scientists and want to understand the speed that you can get to for a given ISP or engine efficiency, where engine efficiency is the energy, kinetic energy in the exhaust divided by the rest mass energy that you use to create that exhaust. That's how I define engine efficiency. Chemistry is down here, 10 to the minus 10, 10 to the minus 11. Ion engines are a little bit higher, but not much. Nuclear engines are up here, but when you want to reach high speeds, so this is the mass fraction ratio. Here are the speeds shown. This is 30% speed light, 10% speed light, going all the way down to 3 kilometers per second. This is chemistry down here. You just can't get there. Okay, so I think what we're going to see is that if you want to get to relativist speeds, there's really only one practical way in the near term, which is going to directed energy. So if you want to get to speeds that are, say, 10% the speed of light, which is here, for payloads that are from 10 kilograms to 1 gram, you're going to be enabled in doing that, but you're going to have very large directed energy systems. This is 100 gigawatts with a sail, which is a micron in green. This is the 10th micron in red, sorry. And this is the speed in meters per second. This is the equivalent beta. So you can get above 10% the speed of light, even for relatively significant masses at the kilogram level, or close to that for kilogram level. But if you want to go to larger masses, you're going to have to go to larger systems. We can also go rapidly to things like Mars. So we could get to Mars with a kilogram in 8 hours. This scales completely differently than chemistry. Or you can get to the moon in about an hour with a kilogram. That has lots of interesting applications. So this is in an upcoming paper that you can look at. But this is not just for wafer scale, which people pick up on immediately. So here's a gram, a kilogram, 100 kilograms. And again, this is the speed of light, 10% speed of light, 1% speed of light. You can get to high speeds. You just have to go to large arrays. This is the array size in meters. Here's 10 kilometers, 1 kilometer. This is the speed in meters per second. Here's the beta. It's too much information to understand. Here's what we're doing in the laboratory. So here's our latest results. This is a 2-element phased array known as a Mach-Zehnder arrangement. We built, in addition to the array itself, we built a custom FPGA to close the loop. Measured all kinds of phase noise and fibers, but we closed the loop. So this is July 27th. We got a 1,000th of a wave closure, which is excellent, with no fiber in. But then we started putting fibers in. So this is a 500-meter baseline. Again, on the same day, we got to a 16th of a wave, lambda over 16, which is good, actually excellent. Here's our latest results as of a few weeks ago. This is the lock duration, which now is indefinite. It seems to work completely. No fiber, 500 meters, 800 meters, and 3 kilometers. And we've now locked all the way out to 3 kilometers. And I have no reason to believe that we won't get to a 100th of a wave at 3 kilometers, but even a 10th of a wave is good enough. So it works great. We're building things in lab. Here's some pictures of things that we're actually building. We're also working on wafer scale spacecraft just for fun, really, because the students like working on this. And I have some in my bag if you want to look at them. Here's a quarter for reference. But in fact, you don't want to build small things. This is a misnomer. You do not want to build tiny spacecraft. That's a complete misnomer because energetics works against you, as does diffraction for laser comm. What you want to build are actually large, low-mass things. So here's our latest nanofab as of last week. This is a silicon wafer reactively ion etched down to a few microns, but with a hexel pattern. It's 0.5 gram for 100 meters diameter, 100 millimeter diameter. And then we're going to hybridize this unit to put 3,5 and other materials on it. And here's a titanium one for reference. We can go even thinner than that, but this is just what we've done so far. This is some work done at Yorktown on ultra-thin submicron wafers. On this one, by the way, just to show you, this can hold 1 trillion transistors on that wafer, which we've already made. We haven't put the trillion transistors there, but we've made the wafer. There's much more coming. We've recently done some interesting work on materials. So I want to show you this really quickly because it's important to those who are interested in materials. It turns out that there's a fundamental limit on the speed you can get to for a given material strength for a given array diameter and wavelength. So this is not yet published, but it's coming out soon. Here's a test chamber with some material. Okay, just about done. This is 500 nanometers thick, so it's basically a few thousand atoms thick. It's a special type polymer, and it worked just about as we expected. It's actually strong enough to just about achieve 10% speed of light. We're building lots of other things. I won't bore you with this. Interstellar communication is a big issue. You can read our papers if you're interested. I'd put it on the moon in the long term. Okay, backside the moon, I think, is the best place to put it in the longer term. But it's not what we're going to do for now. Okay, let me stop there. It's basically one giant hammer for lots of nails. And that's one nice thing about this is you get lots of different things from one system. This, I think, should terrify people, but we're starting a program on sending out biological systems. I will stop, yes. Okay. So this is you in the future, okay? Okay, I see the biggest challenge is, how do you get a group together that stays together for 30 to 50 years? I think it's a major problem that we should discuss. So I'll stop.